prizes, including the Warner Prize of the AAS, and very prestigious prizes. And of course, is now the deputy director of the IOA in Cambridge. So let's hear what he has to say about particle physics with X-ray clusters. Looking forward to it, Chris. Over to you.
Thank you very much, Samantha, and thank you so much for that invitation to come and speak to you. So I'm going to be talking today about how we can use astrophysics to probe particle physics beyond the standard model. And I'll sort of tell the story of how a simple astrophysicist has got into this particular subject. And let me thank up front my collaborators in this work, in particular David Marsh, Helen Russell, and James Matthews. David is a sort of real card-carrying particle physicist who has been my guide in a lot of the more theoretical aspects of this. But then also thanks to my other collaborators too for this field. So to come to the outline of what I'll talk about, I'll just give a quick overview of an astrophysicist's view of particle physics, to sort of set the scene of the problems we're trying to solve. Then this talk is going to be about one particular aspect of particle physics, so-called axions, the axion sector of particle physics. So I'm going to give you an introduction to axions and to axion-like particles. You know, why I'll try to motivate why physicists are interested in axions, and then I'll get into the main part of the discussion today, which is the power that astrophysics has to actually constrain this sector of physics. In particular, I'll talk about how something as simple as the transparency of a galaxy cluster, in particular the transparency to X-rays of a galaxy cluster, is actually a powerful probe of these axions, these axion-like particles. So I'll sort of talk about that and some new results we have from Chandra. And the upshot is that we have the tightest constraints to date on axion-like particles in a particular part of parameter space. And then I'll talk about some future prospects, in particular looking forward to the next generation of X-ray observatories. And just to say, I'm happy to take, if there are any sort of short clarifying questions during the talk, I'm happy to take them. Or of course, there'll be time towards the end to take questions. Okay, so to sort of set the scene about particle physics, of course, we have the standard model of particle physics is an extremely successful theory. It's basically a quantum field theory that explains all of the non-gravitational physics that we have yet seen. And it explains it in terms of interaction between a relatively small number of ingredients. And so over on this chart here, just to ask, can you see my pointer?
Yes, we can. We can see your pointer. Yes.
Okay, good. So yes, it's the standard model has a relatively small number of ingredients. We have the quark sector here, so we have these 6 quarks. We have 6 leptons, you know, the electron, muon, tau, and the corresponding neutrinos. And between them, they basically build up all of the matter within the standard model, and they interact through 3 forces: electromagnetic force, the strong and the weak nuclear force, and then sort of the magic ingredient that makes the whole thing work, and for example gives particles masses, is the Higgs boson. So that is sort of the standard model in a nutshell. I'm not going to talk about the nuts and bolts of it, but it is it's a description of all of the non-gravitational physics that we have seen in the laboratory or LHC, for example, or at CERN. But we know that this is not the complete description of nature. I mean, for a start, the glaring omission here is the standard model does not include gravity. Gravity does not come into play here. And in fact, if you just take the standard model and then you take our best description of gravity, which is general relativity, and sort of just glue the two together, you get all kinds of problems. Interestingly, a lot of these problems actually, are astrophysical in nature. So for example, you put these two together, standard model and general relativity, you end up with actually a quite profound paradox about black holes and information, so-called black hole information paradox, where these two pillars of physics just give you inconsistent answers to what happens to information as it falls into a black hole. In a more practical sense, when you if you have a standard model and general relativity, it gives you no explanation for the non-baryonic dark matter we see. 80% of all the matter we see in the universe is not in is not of a standard form that is explained by the standard model. We see it gravitationally, but there's no explanation for it in the standard model. And then similarly, if you take the standard model and general relativity, there's no explanation for dark energy. There's no explanation for why the universe is accelerating in its expansion right now. So there's clearly problems here. And in addition to this, if you just take the standard model as a standalone theory, it's dissatisfying because there's a large number of free parameters to it. For example, a lot of the masses here and the coupling constants are free parameters. And there's some important fine-tuning problems to it. So to sort of dig into one of these fine-tuning problems, and this is the motivation for axions, there's an extremely important problem that's been identified with the standard model. It's something called the strong CP problem. So what is the strong CP problem? And this is what axions were invented for. So the strong CP problem is the following. You take the strong nuclear force, and experimentally, it obeys what's called the CP symmetry, meaning if you take your system and you flip the sign of all the charges, and then you do a parity inversion, so you sort of reflect it in a mirror, the force is exactly the same. The outcome is exactly the same. Yet there's nothing in the mathematics of the standard model that says the strong force should respect CP symmetry. The standard model tends to take the attitude that what is allowed mathematically should be allowed physically, and yet there is no reason why the strong force should actually respect CP symmetry. So the approach that was taken, or the solution to this problem that was taken in the 70s when it was first recognized, is a very quantum field theoretic solution, which is that you take the offending terms in the theory, in the standard theory, and there are coefficients in there of the CP violating terms, and rather than just arbitrarily set those coefficients to 0, you make them into quantum fields that have dynamics that have naturally decayed to 0. And it was pointed out by Weinberg and Milchek that, so that this was pointed out by Pecci and Quinn, and quite quickly after it's pointed out that if you have a new field, then that gives rise to a new particle. And this is the so-called axiom, QCD axiom. And the reason why, and this is not a joke, this is actually true, the reason why it was called the axiom is that there was a washing detergent at the time in the US called Axion. And this particle will wash away the CP violations from the theory. So that's why it's called Axiom. Now, that's sort of the original motivation for these particles called axions. What are they? They'd be spin 0, so non-spinning, uncharged bosons. That's what would be predicted from this kind of particle. But in fact, these kind of particles naturally arise in modern theories. For example, string theories naturally give you particles that have just these kind of axionic properties. And because the string theory particles, the particles that arise from string theories, do not actually have anything to do with the strong CP problem, they're called axion-like particles. So that's the distinction between axions and axion-like particles. So axion-like particles, again, are these spin 0 uncharged bosons. So that's the particle physics of it. Now, one reason why they might be interesting is that, in fact, they're actually a viable candidate for cold dark matter. Even though, as we'll talk about in a short while, even though these particles can be extremely light, they can have extremely small masses, there can be processes in the early universe that non-thermal processes that generate them in an extremely cold manner. So they can actually be a viable candidate for cold dark matter. And actually, one of my colleagues at the Institute of Astronomy, Anastasia Vyalkov, has been looking at the consequences of having axion dark matter. If you make the dark matter particle, if you make the axion light enough, then in fact the dark matter can actually have de Broglie wavelengths that are of galactic size. So in this model here of a collapsing filament in a structure information simulation, you can actually start to get quantum interference fringes from in the dark matter. So formally, you have to, when you do your structure information problem, you have to solve the Poisson-Schrödinger problem. You have to actually solve the Schrödinger equation as you go. But so that's why axions are interesting, and for that reason, they've become the subject of very intensive searches, including in the laboratory. So how do you go about looking for axions? And you'll see in a while eventually how the astrophysics comes into this. One of the central bits of physics that any of these axion-like particles experience is the following. Suppose you have a photon beam traveling through a magnetic field. Well, in standard model, as long as the photons are not such high energy or the magnetic field is not such high energy that you get QED effects, but in the standard model, the photon beam will just travel through the magnetic field unaffected. If, however, you have axions in your model, there's naturally a coupling term in the Lagrangian that causes the axion field, that's little a here, to interact with the electromagnetic field. And the result is that as the photons are propagating through a magnetic field, they start to convert into axion-like particles, and then vice versa. You have an oscillation between the photon beam and an axion beam. For those who are familiar with neutrino oscillations, neutrino flavor oscillations, the mathematics of this is very similar. That when you, in the new theory, in the extended theory, where you have axions, then a photon propagating through a magnetic field is no longer an eigenstate of, it's no longer an energy eigenstate. And so in fact, you have to put, there's an oscillation between a photon state and an axion state, just in the same way that with neutrino, there's an oscillation between different flavors. So, so this is actually an important way of looking for axions experimentally. And if you, let's just go to this, just to sort of quote a result of an analysis of this system. Suppose you start with a pure polarized photon state and you propagate it through some path length L of a magnetic field B, then there's a certain probability that photon will convert into an axion, and the probability is given by this expression here, where I've defined these terms here. So this big theta is basically something that's proportional to the magnetic field strength and to this coupling constant, this axion coupling constant, G. And then it's got an energy term and mass terms in it. And then this delta effective is essentially a characteristic path length, or 1 over a characteristic path length you go. And again, it depends on the masses of the axions. Omega p here is actually the plasma frequency, so essentially related to the density of the plasma you're going through. And then it goes as 1 over energy. So you have this expression here. Now, if you assume that L is very, very, very small, which it would be in any laboratory experiment, then you can actually just simplify this expression significantly, to, do a small angle approximation here, and you find the probability of converting from a photon to an axion just goes as the square of the product of G, B, and L. So if you have a strong magnetic field and you have as long a path length as you can look for this conversion here. So one of the classic laboratory experiments that's done to look for axions is this one, the so-called light shining through wall experiment. So the idea here is that you have some laser beam, you shine the laser beam through a strong magnet, and then you shine that at a wall. So this dark red thing, imagine that's a big wall that just goes completely top to bottom. And then on the other side of the wall, in a, schematically in a dark room, you have another magnet. You shine another magnet, and then you have a photon detector. So of course, in the standard model, the laser beam runs into the wall and stops, and the photon detector detects nothing. But if there are axion conversions going on, then some of these photons will be converted into axions. The axions will pass straight through the wall. When they enter this magnetic field again, they'll be converted back into photons, and then they'll be detected. So this is one classic way of looking for axions. Another one is to find the most powerful natural axion source we should have around us, which is the sun. And we expect that if axions exist, they'd be coming out of the hot plasma in the center of the sun. And we can make what's called an Axion Helioscope, which is basically you take an X-ray telescope and you put it in a light-proof box with a magnetic field, and you point it at the sun, and you have axions coming out of the sun that have characteristic energies of the temperature of the sun. So the core of the sun is about a 1 keV plasma. So you have roughly 1 keV like axions coming out. They would convert into photons in the magnetic field, and then they'd be focused and detected here. So this is a picture of a real Axion helioscope. This is the so-called, this is the one in CERN, the CAST, the CERN Axion Solar Telescope. And you point, so in here is basically a large volume magnetic field, and then there's an X-ray telescope at this end and an X-ray telescope at this end. And you point this end at sunrise, and you point the other end at sunset, and you look for signals. And this is the current one, and there's a new Axion helioscope in production or being planned, which is the International Axion X-ray Observatory, which is basically an upscoped version of that. So what are the current results from these laboratory experiments? An important sort of plane, an important parameter space that we'll be talking about a fair bit in what comes is this parameter space here. So we have, the name of the game here when you're hunting for a particle like this is to define a parameter space and then just start trying to hack away at it experimentally. So on the x-axis, we have the axion mass, which is unknown. Could be anywhere from a relatively massive particle, say 10 eV, down to much, much lower masses. And then on the y-axis, we have this coupling constant between the axions and the electromagnetic field, axions and photons. So the CERN Axion helioscope that I just showed you the picture of has already excluded everything in this blue region. So we can start to eat away down at this, into this parameter space. And that new international Axion X-ray telescope would reach this point here. And then there are various other experiments on here. I won't go into all of them. There's some great reviews written by Peter Graham, for example, that describes all of this. So I mentioned that there are axions are a natural, or axion-like particles are a natural product of string theory. String theory tends to give you very light axions. So the string theoretic axions would be these very light particles off the bottom of this plot. But these lines here, the way these constraints work, is they all extend down in mass. So the Axion helioscope constraints all extend down here. Okay, so let's now come to astrophysics, since we're astrophysicists. So what can we do here? Well, remember, the name of the game is that if you have axions passing through a magnetic field, or if you have photons passing through a magnetic field, there'll be an interconversion of them, and we can try to look for that. So if we come to galaxy clusters are a very, let's come back. Galaxy clusters are a very interesting system from this point of view. So this is a picture of the Perseus cluster of galaxies. And of course, what you see is a bunch of galaxies. That's why it's called a galaxy cluster. But if, in fact, we know that what we're looking at here is not the bulk of the mass. So what we're looking at here is just the stellar mass in the galaxies. If we look at it with X-rays, then we see that there's a much larger amount of mass, about 3 or 4 times more mass, is actually sitting in the as hot plasma in the gravitational potential well of the dark matter that really dominates the mass budget of this system. So, but even most of the baryons in the galaxy cluster are actually they're not in the galaxies. They're in this hot plasma that fills the space between the galaxies. So, if we look at the properties of this plasma, we find that, or look at the properties in general of these clusters, there's about 10 to the 15, a characteristic cluster, about 10 to the 15 solar masses of dark matter, about 10 to the 14 solar masses of this hot plasma, the hot intracluster medium. It's very tenuous. It's very hot, typical temperatures of a few keV. So put in terms of Kelvin, that would be a few tens of millions of Kelvin. But interestingly, from this point of view, it's magnetized. I'll tell you how we know it's magnetized in a little while, but this gas is magnetized. So clusters of galaxies give us enormous path lengths, of order megaparsec path lengths through magnetic fields. And yes, they're not particularly strong magnetic fields, but in fact, if you just take the product of this length and this magnetic field, you start to become extremely competitive with with the Axion helioscopes. So let's come back to our expression here that I showed you before for the probability of the interaction of the probability of conversion of a photon into an axion. And what I did before was to assume that L is very small, and therefore that this expression became very, very simple. But let's now just scale, let's put numbers into these expressions that are scaled to characteristic cluster, intracluster medium numbers. So what we find now, if we do this, is we find that these thetas are actually of order unity, typically, if you put in typical densities and typical energies, X-ray energies, and say a characteristic coupling constant. And then this effective, with this 1 over the characteristic length scale, this delta effective becomes of order an inverse kiloparsec. So what this means now is that in a cluster of galaxies, we're in an interesting regime where firstly, the coefficient in front of this sign can be not small, it can be easily of order a few %. And secondly, we're into the realm where this sign term is oscillating away. So if we just do a very simple calculations, plotting up some solutions of this for some characteristic numbers for a cluster, just put some characteristic numbers in here, what you find is that the probability of converting from a photon to an axion is going to be energy dependent. It'll oscillate away, and also will grow with energy as you go. So this is the experiment we're going to do, and the experiment I'm going to show you results from is this one. We're going to find an X-ray source in the center of a cluster, and we will look at the X-ray source with an X-ray telescope and look for the signatures of the conversion of those X-rays into axions. And spoiler alert, we haven't found it yet, but what we can do is try to set limits on the signatures, or set limits on the conversion of photons into axions, and thereby set limits on the parameter space for the axions. Now, there's 2 challenges here. One is actually just a very practical challenge, which I'll come to in a second, which is that it actually is quite difficult to take a very high quality spectrum of an X-ray spectrum of an AGN in the middle of a galaxy cluster. The second challenge is we've got to understand something about the magnetic field that we're going through, because it's certainly not going to be a uniform magnetic field. So we'll come to both those challenges in a second, but just to sort of show you, jump ahead a little bit, these are the kind of characteristic probability, characteristic conversion curves you're going to get. And what I'm showing you now on this plot is not the probability of converting from a photon to an axion. It's the probability that a photon survives on its way out. So this is the survival curve of a photon as a function of energy. And you can see that in some of these models here, it doesn't have the nice periodic behavior you saw last time. That's because the field model here is a chaotic one. It's not a uniform field. So firstly, just to briefly say, why is it difficult to get a good spectrum of an X-ray source of an AGN in a galaxy cluster? Well, if we come to Perseus, this is the Perseus cluster of galaxies, very famous cluster. It has an extensive amount of data from the Chandra X-ray Observatory. This is an image from Andy Fabian of the central region. It's a classic object from the point of view of trying to constrain AGN feedback, because there's actually powerful jets from this object, and they are dumping energy into the surrounding gas, and they're heating it up, therefore offsetting some of the galaxy building that would naturally have gone on if it hadn't been for that. But I want to focus right in the center here. And this image that you may have seen before has a little dark spot in the middle of it. And you may think, well, that's where the AGN should be. Why is it dark? It's dark because the detector is completely saturated here. There's actually a powerful X-ray AGN sitting right here. But using simple imaging mode with Chandra, you cannot get a good spectrum of it because the detector saturates through a process called photon pileup. If you were to use another observatory, say the New Star Observatory or XMM Newton, to try to get a high quality spectrum of this AGN in a manner that was not so affected by this saturation, then those observatories have much poorer point spread function, so you get a very blurry version of this image. You'd mix a lot of the intracluster medium emission into the spectrum of the AGN you're trying to observe, and then it wouldn't be a very clean spectrum. So that's why it's challenging to do this. So this comes to the main project I want to talk about. I wrote a proposal, and I got accepted to take a very long Chandra observation of the Perseus cluster of galaxies in what is actually quite an unusual mode for this kind of system, which is with the diffraction gratings in. So you put the diffraction gratings in, and you can kind of see a pixelated, this is just one section of our data, you can see a pixelated version of that cluster in there. These are those cavities you were seeing. And what you see here, these lines are the dispersed spectrum of the powerful AGN that is present at the center. Now, the diffraction grating on Chandra is a slitless diffraction grating, meaning that you diffract everything that is there. So in fact, you also diffract the cluster emission here. So you can see actually that the cluster emission is elongated out in the direction along there. But still, you can go in, you can actually then you can cleanly extract the spectra of the AGN. Just to point out why there are two lines here, there's two different diffraction gratings at play at the same time that cover different energy bands. This is the high energy grating, and then got the medium energy grating. You can extract the spectra of the AGN in a way that is clean. The only disadvantage here is that the collecting area of the gratings is about the size of a large postage stamp. And so you need to observe for a very long time to get a decent spectra. So we observed for 500,000 seconds to get a decent spectrum of this. So, of course, I was actually interested mainly from the point of view of the astrophysics of this. What we found was a remarkably boring spectrum. So the spectrum is quite featureless. This is the spectrum here. And if you fit just a very simple power law to this spectrum, you find that it's power law-like to within a few percent. So about plus or minus 3% are these deviations here. Apart from right here, around 6.5 keV or so, where there are some expected ion emission lines from the AGN. What we have here on the right is just a search for emission and absorption lines through the spectrum. And without going into detail here, basically, we don't find anything that is particularly significant apart from these iron lines here. But so it's a pretty featureless spectrum. So in fact, at first blush, the astrophysics you can do from this is a bit limited. But of course, this is exactly what we need for Axion searches. We now have a very clean spectrum of an AGN in the center of this magnetized ball of gas. And we can go and start setting some fairly tight limits on the presence of deviations from the underlying power law. So well, this plot just shows you, if you take a histogram of the deviations in the power law, that they really are mostly constrained within plus or minus 3%. So we can start to do the modeling of the Axion fluctuations here and compare it to these data. Now, one difficulty here is, of course, to do the Axion modeling, we need to know something about the magnetic field. And without going into, I could talk for a long time about this, but without going into too much detail, the thing that we experimentally know about magnetic fields in clusters of galaxies is that is via the Faraday rotation. So if you look at a radio source, this is actually not for Perseus, this is for another cluster, Abel 2199. If you look at the central radio sources and you look at their polarization angle at different frequencies, different radio frequencies, you find the polarization angle rotates as you go to different radio frequencies. And what we're seeing here is Faraday rotations, the fact that the left and right circularly polarized modes travel at different speeds in as the radio waves travel through a magnetic field. So we can actually use this information to start to back out the strength of the magnetic field, but also you can see in this image that the color map here is the so-called rotation measure. So it's a measure of the integral of the line of sight of the magnetic fields times the density. But you can see that it changes quite significantly as you go across the image. So not only can we say something about the strength of the magnetic field, we also can say something about the fact that it must be variable. There must be spatial structure to it. And this is entirely what's expected because the clusters of galaxies are very dynamic environments. There's a lot of stirring going on. I showed you the image of Perseus with those AGN-driven bubbles. And if you take a plasma, such as the intercluster medium, and you stir it, you're inevitably going to generate turbulence. And this is actually from one of my postdocs, Sergei Komarov, has recently done a very nice high-resolution simulation of driven MHD turbulence in ICM light parameters, and you find indeed that you get quite significant field line tangling in these kind of systems. So what we have to do is to model the Axion propagation through a tangled magnetic field. So what we do, just to sort of briefly talk about this, is we take the Axion propagation problem, which is that trying to follow the coupled photon Axion modes as they propagate through the magnetic field. We break the line of sight up into domains, and we assume and the length of these domains is a coherence length of the turbulence in the cluster, or a guess at the coherence length. And then within each domain, we scramble the field direction, and then we solve the Axion conversion problem through this field. So this gives us one particular realization. So for a particular assumed property of the Axion, for a particular assumed mass and coupling constant, doing this calculation will give us one realization as a function of the random field structure we've chosen. And then we can just do that many, many, many times. We can do 1,000 such realizations of the magnetic field structures. So this is what we do, and we let me just briefly say we have a couple of magnetic field models we follow through with Perseus based upon how we interpret the observed rotation measure in Perseus. So this is actually the Perseus data, and there's rotation measure here down towards the very center of the system, and depending upon whether we treat that as a localized screen or as the bulk of the ICM, we have a couple of different magnetic field models that we carry through. I can talk more about that if there's any questions on it. So what we do then is we calculate libraries of these photon survival curves. So as a function of axion mass and coupling constant, we can calculate example representative photon survival curves. And this just shows you a few. This is for a given choice of axion mass and a given choice of axion mass, a given magnetic field structure, and then scanning through axion coupling constants, you can see how the size of the deviations vary. And then for a given coupling constant, and again a given field structure, we can scan through different axion masses, and you can again see how these curves change. So then what we do is we go through a formal marginalization process where we take these libraries of photon survival curves and we compare them to the X-ray data. And essentially what we have here is we can treat these like absorption curves. So if the AGN has a certain spectrum, then the spectrum will get multiplied by this photon survival curves, and that's what we see. So the exercise we go through is this. We have some AGN spectrum that baseline model is a power law. We then multiply that through by the photon survival curves that generates these wiggles and lumps in it. We put that all through the Chandra response matrix. We compare that to the data, and then we can do our Bayesian statistics and ultimately end up with the probability of a given axion mass and a given coupling constant, given the data, marginalized over the large number of magnetic field realizations that we've done. And just to briefly say, some of the priors on this. Well, I'll talk about that in the next slide. So this is the result for one of our magnetic field models. This is our same parameter space of axion mass versus the coupling constant. And you can see here we've gone to very low masses because we are sensitive to very low mass axions of the kind that string theory, or axion-like particles of the kind that string theory would be generating. So we can exclude at 99% level with our magnetic field model A anything that has axions lower than about 10 to the minus 11 eV in mass, and with a coupling constant above about 6 10 to the minus 13. That is an extraordinarily tight limit on the coupling constant. To talk about the limit from CAST, which is that CERN Axion Helioscope, that was up here. That was up here above 10 to the minus 11. This dotted line here is the future Axion Helioscope, the IUCAA. Now, of course, just to say that, not to say that we have made these laboratory experiments irrelevant, we haven't, because they extend to much higher mass axions. Our ability to, our constraints actually cut off at about 10 to the minus 11 EV. That's connected to the density of our system and the sort of the effective mass of the photon in our systems, the sort of plasma frequency. But again, I can talk about that later if there's interest. So we can really set a very, very tight limit on that. Using our different magnetic field model B, this is the one that assumes the rotation measure is from the bulk of the intercluster medium. Interestingly, we find that our 99% 3 sigma exclusion level is a bit higher up. We can only exclude above about 8 10 to the minus 13. But interestingly, at the 95% credibility range, we actually have a preferred part of parameter space. So we preferred not to be down at 0 at 95% level. So now, taken at face value, you think this is a mild detection of the Axion physics. What's actually going on here? What's actually going on is, if you let me skip back to here, if you look at our spectrum, there are actually wiggles in the spectrum. It's not completely consistent with the power law. There are some wiggles here. And in fact, the Axion models quite like these wiggles. So in fact, if you actually look at the successful Axion models, they track this structure pretty well. Now, knowing how the sausage is actually made, knowing how this spectra actually was made, and in particular, we had to do some of the background subtraction issues that went in there. This is probably at the level of the systematics. So I do not believe, given these data, that we can say that these 2 or 3% wiggles are real, and therefore that we should take the fact that the axions fit them to be serious. But I think that's what's going on. That's why we do in fact have a formal detection at 95% level here. I think really what we're seeing here is we're hitting our systematic floor. So the results are that we've set the tightest limits to date on these light axion light, on the coupling constants, the photon coupling constant, these light axion light particles. It's this. So we've already exceeded the next generation light shining through the wall and helioscope sensitivities at these very low mass ranges. And as I just said, this 95% sort of quotes detection is actually, I think, just due to the calibration uncertainties that we're hitting. Now, to put this into context, why is this an interesting limit? Could be anything. Just to put this, to get a little bit more context here, if you're down at 10 to the minus 19 in this metric, that's 1 over the Planck energy. So we assume that the coupling constant must be greater than 10 to the minus 19 if these particles exist at all. But why is this limit interesting? Well, what you can do, or what others can do, because I'm not clever enough to work on string theory, but there is some interesting work where you can use toy string theory models, and you can try to make some estimates of what the effective coupling constant of the axion-like particles would be from string theory. Now, why do I say effective coupling constant? Because string theory actually predicts there should be a very, very large number of these axion-like particles, not just one, but a whole family of them. And a whole family of these very, very light axion-like particles. And in that case, the coupling constant you measure would not be the coupling constant for an individual particle. It would be the coupling constant for the sum of the whole population in a way that you can define in a fairly rigorous way. And what this recent work by Halvorsen has done is to show that using toy string theories and then projecting or extrapolating those models to where you think a sort of a real live string theory should get to, you can predict that the coupling constants should be these red or these pink histogram regions. So for the 2 different kinds of string theory calculations they've done, they've got, one of them has credible regions mostly above 10 to the minus 12 in this coupling constant, and one has a tail that goes a little bit below there, but generally goes higher. So the limit that we just talked about, our Chandra limit, is this solid bar here. And you can see that we're already squeezing right down on the low end of what these string theory models are projecting. So of course, string theory model, there's no such thing as one given string theory model. String theory is a whole family of models, and there's flexibility here. But I think what you can say is that our limits are already being informative to future string theory investigations. So let's see how many on time. So bring things towards a close. Where is this going in the future? Well, I think fundamentally we need better data, as always, and one of looking ahead, the future of X-ray spectroscopy of these kind of systems is very bright. In development right now is the Japanese led mission GRISM, this is the refly the Hitomi, ill-fated Hitomi X-ray satellite. And this will be a pathfinder for two next generation missions, the Athena mission, which has been under development by the European Space Agency, and then LINX, which is a proposal to the US Decadal Survey for a subarc second X-ray telescope. Both of these will be able to progress these studies significantly further than we can right now. This is a simulation from Athena of a deep observation of the Perseus cluster, and you can see firstly that the simulated, these actually are simulated data. There are error bars here, and you can see that we can the cluster emission. We can now separate out beautifully all the atomic emission features in the cluster emission due to the superior spectral resolution of the Athena instrumentation, and then the AGN that would underlie that, if we take a model where we impose a little bit of axion-like structure on the AGN, so this is something that is kind of right at the threshold of what our current detection is, and then if we fit it with a model that doesn't have axions and look at the deviations, you can see that the deviations are very, very obvious. So provided that Athena can be calibrated, and that's a big question, provided Athena can be calibrated down to this level, then it'll be able to make a dramatic advance in this field. And just literally within the past couple of weeks, the Athena science team has set up a science working group, which on standard model of astrophysical probes of particle physics beyond the standard model, and this will certainly be one of the investigations we'll look at. So to bring things to a close, there's tremendous interest in axions and axion-like particles right now. This is the citation stats for the Petrie and Quinn, the sort of defining paper of this field, and you can see that starting really just in the past 10 years, it's taking off. A lot of this is actually driven by desperation out of the lack of detection of WIMP dark matter. So the interest in axions as dark matter candidates is increasing dramatically because of the lack of detection of WIMPs. But also just the laboratory searches for axions have really sort of reached the interesting places. So I talked about one very particular but very powerful way of looking at constraining axion-like particles using the X-ray transparency of galaxy clusters. And I I showed you results from our recent Chandra campaign, and argued that they're already pushing on string theory predictions. So this is just one of the interesting astrophysical probes of new physics, of physics beyond the standard model. There's many others, but I thought I'd sort of dig deep into this one just to sort of give you a feel for what's going on. And at that point, I'm happy to stop and take any questions that have come up.
Thanks very much. Thank you. Thank you very much. So shall we just go by the hands that are up?
Sure.
We did ask you any questions in between. Shantanu, go ahead. I'm unmuting you.
So I guess just two quick clarification questions. I guess you didn't, what about eRosita? So second question is, if I understood correctly, you have taken high resolutions or like taken a spectra of one cluster, integrating for a long time. What about stacking data from spectra from a large number of clusters and then looking? I mean, that's how I think the 3.5 keV line was found by some group. So I guess, are there problems by stacking?
So thank you. Two good questions. The the main problem here is that this particular experiment we're trying to do necessitates having a clean spectrum of the AGN that's sort of separated from the intracluster medium emission, and you have to really work at it to do that. So IRIS-eta, for example, doesn't typically have it's essentially it's XMM-like spatial resolution. So that separation of the AGN and intracluster medium is difficult. So in that way, it's a little bit different because we're sort of effectively looking at almost an absorption. We're trying to characterize an absorption, if you like, towards the AGN. It's a little bit different to the stacking analysis for the 3.5 keV line, which was just trying to look for an anomalous emission line. Now that said, I think it is an interesting idea to take the small number of clusters for which there are these kind of data I'm talking about now, and not necessarily just stack the spectra, but stack the constraints that we get. I mean, you can stack the constraints in a Bayesian way, and I do think that is actually something that is an interesting route forward with the current data. So yeah, no, thank you for that question.
Thanks very much. Thanks, Chris. We have some other questions. I can see a hand up from Suchetana Chatterjee. Suchetana, go ahead. I've unmuted you.
So,
yes.
Hello, can you hear me?
Hello, yes, I can hear you, yes.
Oh, nice talk. So can you please go to the slide where you are showing how you do so you take your spectra and you add the photon Axion coupling, and then yeah, that's right.
Okay.
Now, so this is so the power law is your AGN spectrum, right?
Yeah.
And then you have the ALP, the Axion photon coupling onto it.
Yeah.
And then you just pass it through the Chandra pipeline, or the like a mock simulation kind of thing. You make the Chandra spectra.
Yeah.
My question is that what are the scales? Because when you have the photon Axion coupling, there are these scales involved, right? I mean, so this is the AGN sitting at the center, and I'm expecting that we're talking about the magnetic field of that AGN. And then there are a lot of these, if there are Axion particles, then the X-ray photons, they're going and coupling with the Axion. So I'm just curious about the scales that are involved in this problem. Like because I remember that because depending on the mass and other parameters of the Axion, you'll have certain mixing scales involved. So I'm just curious to know how does that compare with the scales of the AGN.
You mean spatial scales?
Yes, that's right. Spatial scales.
Okay. No, thank you. It's good question. Very good question. So yes, you're right, Theo. If you think about the life of an X-ray photon, sort of leaving the AGN, there's different structures it goes through. It goes through any magnetic field associated with the accretion disk and
Yes.
jet region of the AGN. It'll then go through the magnetic field of the cluster of galaxies.
That's right.
And then even very close to us, it goes to the magnetic field of our galactic halo, as it comes to us. And in principle, every one of these structures could imprint some signal.
Signatures. Yeah.
Now the expectation is that the fields around the AGN itself, even though they're quite a bit stronger, the path length through them is probably not high enough to make that competitive. Now I say probably, it's unclear, but it could be that that there's not enough path length through it. When it comes to a galactic halo, in fact, we may actually be missing that piece of physics there. Our galactic halo may actually be relevant at the level we're talking about now. One way to think about this, however, is that anything like that, either the galactic halo or the AGN field that we're missing would imprint additional structure on it. So in some sense, we're being conservative by just worrying about the magnetic field of the intercluster medium and not worrying about the magnetic field locally to the AGN or locally to us, we're being conservative. If we were to put those fields in as well, we would further increase the axion conversion probability, and we would increase the structure that was on the imprinted on the spectrum, and that would make our ability to detect these signatures even stronger. So
that part that's right. And but then my other point is that wouldn't also we have the scales of these magnetic fields, as you said, and then we also have the mixing scales of the photon and the axion, and that would depend on the parameters of the axion itself, right? I mean, if I go to your equation of the mixing angle and all that, so I was just thinking that how does those compare with because that also is mass parameter, or I don't know, the interaction parameter, if I see your equation before. But thank you. Yeah.
Yes, no, you're quite right that I mean, let me show you two things. Firstly, let's bring up this, because this is what we actually do. We have these cells that we argue are kind of a coherence length of the field. So there's reason to believe from rotation measure that these cells should be a few kiloparsecs each. Now, what you're asking is, how does that scale compare with the typical scale over which this conversion would take place?
That's right.
And it's a very good question. The answer is dependent upon the energy of the photon and the parameters of the axion. In most of our cases, the scale on which the photon conversion is taking place would be moderately longer, but not much longer than these coherence lengths. And in fact, that's kind of the regime we sort of want to be in, because if we were in a situation where the scale of conversion was much shorter than this, we would be starting to be affected by our assumption that this field is uniform in this region.
That's right.
We get these oscillations going here, and then we'd connect it onto some oscillation going there. This is actually something which James Matthews, one of my postdocs, we've been bothered enough by this very question that we've been looking quite carefully at it, and we don't have final conclusion yet, but just to show the kind of thing he's been doing. This is one plot I skipped over. He's been looking at simulated boxes of magnetic field, of tangled magnetic field, and then looking at, suppose we then treat this as a bunch of domains, and we do our axion calculation through it. How does the results depend upon how big the domains are? When do we converge? And what we find is that this plot here, this resolution is the size of our domains that we pick for this particular choice of parameters. And what you find is that you need to be, this is the converged region here, where the answer doesn't depend upon the resolution. So you do need to be sufficiently resolved to start to get the answer. But it's all, again, it's actually in the sense that if you are unresolved, your answer is conservative. You underestimate the probability of conversion typically. That's what we're finding. But it's a very good question, and something which I don't think has really been fully worked out by anybody yet.
Thank you very much. It's fantastic. This is very exciting work. Yeah, thank you.
Shumat, are you there? Maybe
I think.
Sorry, I was muted. Kandu, go ahead. Thanks, Shititana, for your question.
Okay. Yeah, my question I had two. One was related to what Suchetana was saying, because how sensitive it is to a magnetic field model. Because as galaxy clusters have very high conductivity but very low viscosity. So the magnetic Prandtl number is very large. even after taking, if you take collision-less effects and all that. So no simulation is at that regime at present. We
Yeah.
are at the best at regimes of about 10 or 100 or something for the magnetic Frankel number.
Absolutely. Yeah.
So how, since you're making very important conclusions, the question is maybe just to at least the coherent scale of the field, if I make it smaller and smaller, what would happen to your limits? It's
a good question. So so without having done it, this would just be intuiting it through. An important constraint here are the rotation measures.
yeah.
That basically gives you an integral constraint on the field. And the smaller the coherence lengths, the more reversals you have along the line of sight.
Yes.
So in fact, for a given rotation measure, as if you have smaller and smaller coherence lengths, you need stronger and stronger fields.
Right.
In order to, in order to that once you average them all out, you get the right rotation measure, and that would tend to increase the signal we're seeing. So in fact, to the extent that our results are vulnerable to the assumed field, it's actually going the other way. If the field was extremely ordered,
yes,
then you can weaken our results significantly.
Okay.
And in fact, there is actually a paper. I mean, there's a little bit of discussion in the Axion literature about this, where it's been pointed out, sort of fairly somewhat obvious assertion that if the field in Perseus was very, very ordered, I suppose it's basically a not quite uniform, but suppose it was something close to uniform through the cluster, then our limits would be much, much weaker. And that's true, but I don't think that's a very physical.
Okay, interesting. But the other question which I had is, suppose you have X-ray AGNs behind the cluster. Aren't there many such things where the spectrum could be better or equally
Absolutely
interesting?
So if we had a very, very high quality spectrum of AGN behind the cluster, this exactly same physics would work. And in fact, there's other strands of literature which try to do, or which apply these same basic techniques to the gamma ray emission of distant blazars. If you were to sort of stare at the expressions I gave, if you made the field much weaker, so you made the field characteristic of intergalactic field strengths, but if you upped the photon energy to gamma rays, then in fact you similarly become sensitive. So in that case, they have a background object, a background blazar going through the intergalactic magnetic field, and they set sort of similar, they can set limits as well. They're not as strong as our limits because the gamma ray data is not as as high quality, but yeah, it's
very interesting and nice talk. Thank you.
Thanks very much. Thanks, Chris. There is one last question that we'll go to. Indulekha had a question. Go ahead, Indulekha. I've unmuted you. Go ahead, Indulekha.
Yeah, I was just wondering if the presence of relic radio lobes along the line of sight, how much would it contribute to, how much would it change the fact we are using simulations of driven MHD turbulence.
Yeah.
How would adding a relic radio lobe to this plasma distribution, what would it do?
Excellent question. I think the main thing that a relic radio lobe would do for you is to give you an extra diagnostic of what the magnetic field is. Our approach so far has been to mainly just constrain our magnetic fields using rotation measures. But if we do have relic radio structures that we can start to try to make it, try to estimate the magnetic field strength in that structure, then that gives us the nuller constraint on the field. So I think that's in terms of the physics, it doesn't change all that much. It's just yet more magnetized gas along the way. But I think in terms of our ability to diagnose the magnetic field structure in the galaxy cluster, it could be very, very important. Yeah.
Thank you.
Thanks very much. Thank you. And if there are no other questions, thank you very much, Chris, for this.
You're welcome.
This
Yeah.
colloquium. We can't applaud you, physically, but Zoom shows us how to applaud.
Yeah.
And I hope everybody here. You had more than 100 people attending your talk today.
Oh gosh.
And that's wonderful. Thank you very much again. And I'll have to go, but Kandu, you can take over and finish this off. Thank you.
Yeah. Thanks a lot, Chris, and thanks to Dipanjan also, who had this brainwave of trying to get you to give a talk. You should come here physically at some stage.
I would very, very much enjoy that. Yes.
Yes, please.
I go to India fairly regularly, at least when it's not locked down. So I very much enjoy it, and thank you very much for the invitation. It's been a lot of fun to talk to you.
Yes, I'm sure that many people have questions, but they will probably write to you or something like that.
I'd be happy to respond. Yeah.
Yeah. Thanks a lot, Chris. Thank you.
Okay,
I can applaud like this.
Thank you.
Thank you.